We have seen how useful the concept of a reaction norm is in analyzing life history evolution. However, reaction norms occur in many traits. They're a general feature of trait evolution and trait response to the environment. Therefore, we should take a look at what a patient is in terms of phenotypic plasticity. And the conclusion is that a patient is a point on a reaction norm or a reaction surface. In other words, we see one possible realization of that individual, and behind it, there are a host of other possible ways that that particular genotype could have turned out depending upon the environment that it encountered. Patients have individual developmental histories. Their genotypes interact with those particular histories to produce the phenotype. There are evolved rules that govern those interactions, and those rules determine the reaction norms that are produced. And here is an abstract way of trying to visualize what's going on. We owe this to Dick Lewontin from his 1974 book. And what he pointed out is that evolution involves a regular alternation between what he called a genotype space and a phenotype space. Those are abstract concepts. You can think of the genotype space as information and the phenotype space as matter. The first transition that goes on is the one between a fertilized zygote and an adult organism. That's transformation T1. That's development, all right? There, genes are interacting with environments to map the information in the genotype into the material of the phenotype. So that's where reaction norms come in. But let's step through these others just to get a complete picture of what's going on. T2 basically takes the phenotypes that survive and mature and maps them into the phenotypes that successfully find mates and reproduce. That's ecology and behavior. Okay, so that determines who survives and reproduces. T3 is a combination of mating, reproduction, and some of genetics. It determines which array of gametes is then produced to form zygotes. T4 is genetics and reproduction. Basically, that's the Hardy-Weinberg law that determines, given this frequency of gametes in one generation, what is the frequency of zygotes in the next generation. All of this is captured in Lee Van Valen's phrase that evolution is the control of development by ecology. And I think that another take-home message that you can get from this is that you can't change phenotypes without changing development. Development is an essential part of evolution. Now, if we look at an abstraction of development, and that's the reaction norm approach, we can see certain important things. For example, if we graph size of maturity against temperature, in many organisms, the warmer it is, the smaller they are when they mature. The colder it is, the bigger they are when they mature. They grow more slowly and they grow to a larger size at cold temperatures. That would be one reaction norm. You can think of it as a function that maps the genotype onto the phenotype as a function of the environment. And it is a property of a single genotype. If we look at a population is then a bundle of reaction norms. There's one reaction norm for every genotype in the population. And we can take a mean of that, and we can imagine that there is a population mean reaction norm. That would be the average plastic response of that population to the environment. There's another term that's often used. It's been mentioned, canalization. Canalization is the tendency of the developing phenotype to resist perturbation. And some people make the mistake of thinking that canalization and plasticity are opposites, or that somehow they're mutually exclusive. But these diagrams are intended to show you that they're not. Here we have, on the left, a more canalized set of reaction norms, and in the middle we have less canalized reaction norms. In both cases, we have plastic traits that are responding to the environment, but these traits are all doing so in a very narrow band of possible responses, and these are scattered much more widely. So if these happen to be two populations of the same species, we would probably assert that these had undergone selection to canalize the trait. If we were to see this kind of a pattern, where there was one particular environment in which all of the reaction norms came together and were tightly clustered around a point, whereas they diverged much more widely for other environmental values, we would be prompted by seeing that pattern to think, oh, it looks like there probably had been stabilizing selection in this environment, and that may very well have been the one most frequently encountered. Maybe these other environmental values are only encountered rarely and don't make so much difference. So this is also part of the power of this kind of analysis. Now, if we look across all of the traits in an organism, we see that organisms are mosaics of traits, and that some traits have quite different properties from others. So for example, let's just take number of digits and plot it against population density, say for humans or rats or frogs or any other tetrapod. Here are three different genotypes. The lines have been separated just so that you can see that there are three different genotypes. In fact, they're all lying exactly on 5. The number of digits is not varying with population density. However, look at fecundity. Same three genotypes. G1 has high fecundity at low density, and it has the lowest fecundity at high density. It's the most sensitive to a change in population density. Its sensitivity is expressed by the slope of its reaction norm. G3 has the lowest fecundity at low density and the highest fecundity at high density. It is the least sensitive to changes in the environment. If you were to look at low density, you would see genetic variation in fecundity, and at high density, you would see genetic variation in fecundity, but at medium density, you wouldn't see any. You wouldn't realize that there was any genetic variation in the population because they all have the same fecundity at medium density. There is also a relationship between patterns and reaction norms and what we call genotype by environment interactions. Here we have 3 parallel reaction norms. Now, they are all exactly equally sensitive to changes in the environment because they all have the same slope. So they're not interacting with the environment. The genes are not producing qualitatively different reactions. It is true that one of them has a higher mean value than the other, but that relationship doesn't change across environments. Here we have a very strong kind of genotype by environment interaction where the reaction norms are actually crossing. And that can cause all sorts of complications in a heterogeneous environment. One of them is that in certain environments, you can see genetic variation, and in others you can't. So here is an environment which is generating variation in the phenotype. This is genotype 1, this is genotype 2. If we simply use the reaction norm as a mirror to reflect genetic variation over here onto the phenotypic axis, this environmental variation gets translated into 2 distinct peaks of phenotypic variation. However, if we are sampling down here near the point where they cross, the environmental variation doesn't separate the phenotypes of the genotypes on the phenotype axis. And I think that brings home that, in fact, reaction norms are transformers. They take the genetic information, they transform it into a distribution of phenotypic variation as a function of the environment, and in the process, puzzling relationships like this can occur and do occur. For example, it's quite possible that this might be nature and this might be laboratory. And laboratory inference would be very poor at predicting what would be going on in nature. This extends even to the interpretation of genetic correlations. Genetic correlations can actually change sign depending on the environment. And where there's a change of sign in something like a genetic correlation or genetic covariance, then a developmental mechanism the controls over plasticity, that mechanism is strongly modulating the expression of genetic variation. And that can produce indirect selection with surprising effects. So in some environments, you might be selecting for a trait that would cause a correlated increase in the other trait. And in other environments, selection for an increase in one trait would cause a correlated decrease in that trait in the other environment. Okay? So at an environment's intermediate, selection on one trait might not be correlated with any response in the other one at all. This becomes very important when we're now thinking about evaluating the effects of trade-offs, because one definition of trade-off is genetic correlation. And basically this is saying that a correlation can change from positive to 0 to negative across a range of environments, meaning that trade-offs are changing in the same way. Here's an example. This is the larval period, how long it takes tadpoles to develop for spadefoot toads. And this is their body length when they come out of the pond. And if they're living in short-lived ponds, the relationship is negative. And if they're living in long-lived ponds, the relationship is positive. These lines are connecting families of frogs that were divided at birth, half of them put into a short-lived pond, half of them put into a long-lived pond. So there are 1, 2, 3, 4, 5 families here. And you can see that here we have a negative interfamily correlation, and here we have a positive interfamily correlation. This is another case. These are now fruit flies that are being reared in different yeast concentrations. This is their age when they eclose. This is how heavy they are when they eclose. There are actually sets of offspring derived from mothers who are reproducing asexually in this graph, and they have been mated to 5 different males, and then they reproduce. After that reproduction, their grandchildren are being produced asexually. So we have clonal control here. And what you can see is that there is a positive genetic correlation when they are well-fed and they are growing rapidly. And there's a negative genetic correlation here when they're poorly fed and growing slowly. And those are correlations between half-sibs. 2 sets of half-sibs in this case. So genetic correlations can change with environment. The consequences for trade-offs are that the correlations among traits can change from population to population, with populations over time, as gene frequencies change, and during the course of development, and from environment to environment. The responses to selection that are important to life history evolution and to trait evolution in general change in all the same ways. Here's an example from humans. So here are 2 identical twins. This is a human, 2 members of a human clone. Otto ran distance, Evald lifted weights. He started at age 18. Here it's 4 years later, they're age 22. Look at the difference in their phenotypes. These are very different looking people. And that is entirely a plastic response to exercise and diet. So reaction norms, which perhaps were amusingly illustrated in the previous slide, actually have an important role in the origins of health and disease. Variation in early life experience has many consequences. Thin infants are at increased risk of cardiovascular disease, diabetes, and obesity in late life. That's called the metabolic syndrome. Infants who are born by C-section are at increased risk of atopies and obesity. Atopies are asthma, allergies, and eczema. Children who have antibiotic treatments before the age of 2 are at greater risk of obesity and allergies. These are being mediated by the microbiome. So early life experience sets up the microbiome, which is then mediating allergies, autoimmune diseases, and obesity. These are reaction norms. These are responses of genotypes to variation in the environment. So, to summarize, the expression and the development of many traits is sensitive to the environments encountered. It's useful to have this idea of a reaction norm in your intellectual toolkit because it helps us to analyze how genes and environment interact to produce phenotypes. Reaction norms are properly defined properties of genotypes. In humans, it's easiest to visualize them as differences that develop between identical twins that are experiencing different environments. Many medical conditions in adults are sensitive to environments encountered early in life, sometimes quite early in life. Their genotypes interact with those particular histories to produce the phenotype. There are evolved rules that govern those interactions, and those rules determine the reaction norms that are produced. And here is an abstract way of trying to visualize what's going on. We owe this to Dick Lewontin from his 1974 book. And what he pointed out is that evolution involves a regular alternation between what he called a genotype space and a phenotype space. Those are abstract concepts. You can think of the genotype space as information and the phenotype space as matter. The first transition that goes on is the one between a fertilized zygote and an adult organism. That's transformation T1. That's development, all right? There, genes are interacting with environments to map the information in the genotype into the material of the phenotype. So that's where reaction norms come in. But let's step through these others just to get a complete picture of what's going on. T2 basically takes the phenotypes that survive and mature and maps them into the phenotypes that successfully find mates and reproduce. That's ecology and behavior. We have seen how useful the concept of a reaction norm is in analyzing life history evolution. However, reaction norms occur in many traits. They're a general feature of trait evolution and trait response to the environment. Therefore, we should take a look at what a patient is in terms of phenotypic plasticity. And the conclusion is that a patient is a point on a reaction norm or a reaction surface. In other words, we see one possible realization of that individual, and behind it, there are a host of other possible ways that that particular genotype could have turned out, depending upon the environment that it encountered. Patients have individual developmental histories